Welcome to the deep dive. Today, we're looking into something pretty fascinating, actually. Unexpected land movement in places like Germany and South Africa.
Yeah, it's a surprising link between the ground itself and water, or rather the lack of it.
Exactly. And if you're tuning in wanting to get a solid understanding of important environmental shifts, well, this is definitely for you. We're diving deep today.
We'll be drawing mainly on research from the University of Bonn they published in the Journal of Geophysical Research, Solid Earth, and also using satellite data from the GRACES mission, reported by SciTech Daily.
Right. So our mission really is to unpack this unexpected connection. How can drought, losing water, actually make the land rise?
It sounds counterintuitive, doesn't it?
It really does. Okay,
Yeah.
so let's start with the initial observations. What first tipped scientists off? I gather it started in South Africa.
That's right. For quite a while now, they've had this network of permanent GPS stations across South Africa. Really precise stuff.
For mapping and things like that.
Yeah, surveying, plate tectonics, that sort of thing. And they noticed that in some regions, the ground was slowly, gradually rising.
Rising. How much are we talking?
Up to about 2 millimeters per year in certain areas, which might not sound like much, but geologically, it's noticeable.
Okay, 2 millimeters a year. And you mentioned Germany, too.
Yes, a separate German study found something similar there. Land rising by about 6 millimeters total between 2012 and 2020. Different timescales and amounts, but the same phenomenon, uplift.
Okay, so for South Africa, what was the thinking before this new research? Why did scientists think the land was rising?
Well, the dominant theory for a long time involves something called mantle flow, specifically a mantle plume.
Right, okay. Mantle plume. Remind me what that is exactly.
So think of the Earth's mantle, the layer beneath the crust, as this incredibly hot, thick, slowly churning rock. A mantle plume is like a specific upwelling, a sort of tube of hotter material rising from deep inside.
Ah, okay, like a hot spot under Hawaii or something.
Similar idea, yeah. And the theory was that this rising plume under South Africa was pushing upwards on the crust from below.
Making it bulge, essentially.
Yeah, exactly. That upward pressure was thought to be the reason for the land slowly rising. A deep geological process.
Makes intuitive sense. A big push from deep down. But the University of Bonn research suggests maybe not.
Precisely. They came forward with a different hypothesis. They suggested that maybe the main driver isn't this deep mantle activity, but something happening much closer to the surface.
Which is?
Drought. The loss of water. Both groundwater, water stored underground, and surface water in rivers and lakes.
Wait, losing water makes the land go up. That still feels backwards.
It does. But listen to what Dr. Makan Karagar from the Bonn team said. We believe that the loss of groundwater and surface water due to droughts may also be responsible for the land rising. It's a pretty significant shift in thinking.
Okay, I need to understand how they got there. What evidence points towards drought instead of mantle plumes?
Well, one key thing they did was look closely at precipitation patterns across South Africa over time. Rainfall data, basically.
And what did they find?
They found a really interesting correlation. The regions that experienced the most severe, the most prolonged droughts,
Yeah.
those were also the regions where the GPS stations recorded the biggest upward movement, the most uplift.
Ah, okay, so less rain, more uplift.
Yeah.
That's a direct link they observed.
A very clear link, yeah. That was a strong piece of the puzzle.
And they didn't just rely on ground measurements, right? You mentioned satellites?
Correct. They brought in data from the GRACE mission. That stands for Gravity Recovery and Climate Experiment.
GRACE. Okay, what do those satellites do? Measure gravity.
In essence, yes. They fly in tandem and measure tiny variations in Earth's gravitational pull as they orbit. These variations are often caused by changes in mass on the surface.
And water has mass, obviously.
Exactly. So changes in gravity can indicate changes in the total amount of water stored in a large region, surface water, soil moisture, and, crucially, groundwater. Christian Milka, another researcher on the project, mentioned using this GRACE data specifically to calculate changes in this total water storage.
But I remember hearing GRACE data is quite broad, isn't it?
Yeah.
Like it doesn't pinpoint small areas.
You're absolutely right. Spatial resolution is pretty coarse. We're talking several hundred kilometers across, so it gives you a picture over a large area, like a big water management zone or even a small country, rather than a specific town or field.
So how did they use that broad data to support a theory about specific GPS station movements?
Good question. Even though it was broad, they could compare the trends. They looked at these large planting zones in South Africa. In zones where grays showed a significant decrease in the total water mass over time,
Uh-huh.
the GPS stations within those same zones generally showed higher rates of uplift. So the large-scale water loss matched the pattern of localized uplift. It provided supportive evidence even with the resolution limit.
Okay, so GPS shows uplift correlating with drought locally, and GRACE shows it correlating with water loss regionally. But they needed something more precise,
Yes, to really nail it down, that's where hydrological models came in. These are complex computer simulations of the water cycle.
like modeling rainfall, runoff, groundwater flow, everything.
Exactly. And crucially, these models can be run at a much higher resolution than GRACE. Think zooming in, looking at much smaller areas, and how water changes there.
And what did the models show?
Well, according to Christian Mielke again, these high-resolution models strongly supported the drought hypothesis. They showed that the amount of land uplift observed could largely be explained just by the loss of water mass due to drought conditions.
So the models basically said, yep, losing this much water would cause the land to rise this much.
Pretty much, yeah. It tied the observations and the theory together quite neatly.
Okay, I think I'm getting the evidence. But let's go back to the why. Can you explain the mechanism again? How does removing water weight make the solid ground bulge upwards?
Right, the mechanism. The easiest way to think about it is maybe like a big piece of foam or a sponge.
Okay.
Imagine that foam is saturated with water.
Yeah.
It's heavy, right? And compressed under that weight.
Yeah, makes sense.
Now, what happens if you squeeze the water out or let it evaporate?
The foam expands. It springs back up.
Precisely. The Earth's crust, while it seems rigid, actually has some elasticity. It responds to load. The sheer weight of water on the surface in lakes and rivers, and especially the vast amounts stored as groundwater, exerts significant pressure, a huge load on the crust.
So drought removes that load.
Exactly. During a drought, you lose surface water, soil moisture dries out, and groundwater levels drop. That massive weight is reduced. And just like the foam ball or sponge, the underlying crust can then rebound slightly, bulging upwards in response to the reduced pressure.
That foam analogy really helps click it into place.
Wow. So this isn't just a geological curiosity. It has real-world implications, right?
Okay.
Especially for droughts. Absolutely huge implications. One major suggestion from the researchers is using this effect. We already have networks of these permanent GPS receivers.
Yeah, the ones they used for the study.
Right. They're already there for surveying, plate tectonics monitoring, etc. The idea is these could become a relatively cheap and less effort-intensive way to monitor droughts.
How so? By tracking the uplift.
Yes, because the uplift is a direct response to water loss, particularly that hard-to-measure subsurface water loss, the groundwater. Tracking how much the land rises could give us a really good indicator of how severe a drought is becoming, especially in terms of depleting those hidden underground reserves.
That's clever. Using land movement as a proxy for water loss.
It could be a very valuable tool.
And does it extend beyond just monitoring natural droughts? What about water we take out?
Definitely. The same principle applies. If you're pumping out huge amounts of groundwater for agriculture or for cities or industry, that also reduces the load on the crust.
So the GPS data could potentially show the impact of groundwater extraction too.
Yes, it could provide insights into how quickly reserves are being depleted by human activity. That kind of information is vital for, sustainable groundwater management.
Making decisions about water use, maybe even rationing in some areas.
Potentially, yes. It gives water managers another data point to understand the stress on the system.
And this all feels incredibly relevant with, well, climate change happening.
It's directly linked. Climate change is predicted to increase the frequency and severity of droughts in many parts of the world. Precipitation patterns are changing. Water scarcity is becoming a much more pressing issue globally.
You just have to look at examples like Cape Town a few years ago.
Exactly. Cape Town's Day Zero scare between 2015 and 2019 was a stark warning. The very real possibility of a major city running out of water. Understanding all the factors involved, including these subtle land responses, becomes crucial.
And for our listeners, maybe particularly those preparing for something like the UPSC exams in India, this seems like a perfect example of interconnectedness.
Absolutely. This research sits right at the intersection of several key areas. You've got geography, landforms, climate patterns, you have science and technology, the GPS, the gray satellites, the modeling, and critically, environmental studies, resource management, climate change impacts, water security.
It really ties together syllabus topics. Understanding these complex feedbacks is important.
Definitely. It's not just about isolated facts, but seeing how these systems interact, how climate impacts water, which impacts land, which we can measure with technology, which then informs policy. That's the kind of integrated understanding useful for mains and even prelims.
Okay, so let's boil it down. What's the single biggest takeaway from our deep dive today?
I think the main thing is this surprising discovery. Drought and significant water loss can physically cause the land to rise by measurable amounts. It challenges older geological explanations in some cases and shows just how powerful the influence of water is, even on the solid Earth.
And it highlights the potential of technologies we already have, like GPS, to help us monitor really critical environmental issues like drought severity and groundwater depletion.
Which are only becoming more important in our changing climate.
So here's something to think about. How could these findings actually change the way we manage water? How might they influence policies for drought preparedness, especially in water-stressed regions, maybe even in India?
Yeah, and for those focusing on UPSC, consider how does this specific research connect to India's own water security challenges? Think about groundwater depletion in the Punjab or drought patterns across the country. How does this add to your understanding of environmental management and sustainable development themes?
Definitely food for thought.
Mhm.
If you found this discussion useful, please do like, subscribe, and maybe drop a comment with your own questions or insights on this. We'd love to hear from you.
And just to reiterate, the reporting from SciTech Daily on the University of Bonn's research was a key source for our discussion today. Thanks for joining us for this deep dive.